A system's response shape as a function of frequency is a common way to categorize systems and specify design requirements. These types of systems are called filters, and they're the subject of this video. It's common to characterize circuits and other systems according to the shape of their magnitude response. In general, the characterization is based on identifying ranges of frequencies where the magnitude response is high and where the magnitude response is low. When the magnitude response is high, the output amplitude will be high relative to the input amplitude. At these frequencies, the input signal is said to be passed through the system, since the input signals at those frequencies will be readily apparent in the output. This range of frequencies is called the pass band. In other frequency ranges, the output amplitude will be low relative to the input amplitude. For these frequencies, the magnitude response is small relative to other frequencies. Since input signals at those frequencies will not be readily seen in the output signal, the input signal is said to be stopped by the system, and this range of frequencies is called the stop band. As I've mentioned, circuits are often categorized according to their effect on different frequency ranges. These types of circuits are called frequency selective circuits, or filters, since some frequencies are filtered out or stopped by the circuit. Next, we'll talk about some special cases of magnitude response shapes. The first category is called a low-pass filter. As the name implies, these types of circuits pass low frequencies and stop high frequencies. I'll introduce the basic terminology in the context of what's called an ideal low-pass filter. An ideal low-pass filter allows all signals in the low frequency range to be passed by the circuit with exactly the same magnitude response. All signals in the high frequency range are completely stopped by the filter, so the magnitude response in this range is 0. The magnitude response is piecewise, so that the transition between the pass band and the stop band is abrupt. The frequency at the boundary between the pass and the stop bands is denoted as omega sub c and is called the cutoff frequency, or sometimes the corner frequency. By definition, the so-called low frequencies are those frequencies below the cutoff frequency, while high frequencies are above the cutoff frequency. This is an ideal filter because of the sharp transition between the pass band and the stop band. This sudden shift in magnitude isn't possible for any real-world circuit. Any circuit we can actually build will have a smooth transition between the pass band and the stop band. Our second case is an ideal high-pass filter. High-pass filters pass high frequencies and stop low frequencies. An ideal high-pass filter has a magnitude response that looks like this. All the low-frequency inputs are completely eliminated by the filter, and high-frequency inputs are passed through with exactly the same multiplicative factor. As with low-pass filters, the transition frequency between the pass band and the stop band is denoted by omega sub c and is still called the cutoff frequency or the corner frequency. We'll only be concerned with low and high-pass filters in this course, but there are a couple of other common filter types I want to mention in passing. Band-pass filters pass an intermediate range of frequencies and stop frequencies both above and below this frequency range. The reverse situation is called a band-stop filter. An intermediate range of frequencies is stopped while frequencies both above and below this range are passed. This type of filter is also called a notch filter, since the magnitude response looks like it has a notch taken out of it. Next, I'll mention a few basics relative to creating physical circuits that implement filtering processes. Filters are often described by the order of the differential equation relating the input and output signals. For example, a first-order filter is implemented by a circuit that's governed by a first-order differential equation, and a second-order filter has a second-order differential equation relating the input and output. Low and high-pass filters can be implemented with a first-order or higher circuit. In order to implement a band-pass or band-stop filter, you need at least a second-order circuit. In this class, I'll only cover first-order filters, so we will only be concerned with low-pass and high-pass filters. Next, I'll revisit a couple of circuits we've analyzed in previous videos in the context of filtering. My first example will be this RC circuit. The input is an applied voltage, and the output is the voltage across the capacitor. This is the frequency response we calculated, and this is a plot of the magnitude response for the circuit. At low frequencies, when omega is equal to 0, the magnitude response is 1, 4 over 4. And at high frequencies, as omega goes to infinity, the magnitude response goes to 0. This is a low-pass filter. The magnitude response is high at low frequencies and low at high frequencies. As we'd expect from a real circuit, the transition between the pass band and the stop band is smooth. This circuit is my second example. The input's a voltage source and the output is the inductor voltage. This is the frequency response, and this is the plot of the magnitude response. The response is low at low frequencies and high at high frequencies. So this is a high-pass filter. Input signals with high frequencies are present in the output, while low-frequency inputs are eliminated from the output by the circuit. Again, the transition between the pass band and the stop band is continuous. As we saw in our previous examples, there's a gradual change in the magnitude response between the response at low and high frequencies for any real filter. This introduces another problem. How do we define the cutoff frequency if the difference between the pass and the stop bands isn't obvious? The solution is that we just have to make a rather arbitrary definition of where the cutoff frequency is and then standardize that choice. By general consensus, the cutoff frequency is defined as being the frequency at which the magnitude response is 1 over the square root of 2 times the maximum value of the magnitude response. This is all you really need to know about how the cutoff frequency is defined, but I do want to give a little justification for this choice. Circuit input and output signals are usually voltages or currents. For a resistor, power is proportional to the square of the voltage or the current. It's I squared times R, or V squared divided by R. If the voltage or current of a resistor is reduced by 1 over the square root of 2, the power will be reduced by half. Very roughly speaking then, the cutoff frequency is the frequency where the filter reduces the output power to half of its maximum value. For that reason, the cutoff frequency is sometimes referred to as the half power point. As I mentioned before, this tidbit of information isn't terribly important from an application standpoint, but it is sort of nice to know that the definition is not completely arbitrary. Next, let's determine the cutoff frequency of the circuits in our previous examples. For our previous RC circuit example, we determined that this was the magnitude response of the circuit. The maximum value of this magnitude response was when omega was equal to 0, and that response was 1. So the magnitude of h of j omega maximum is equal to 1. The magnitude response of h of j at the corner frequency, omega sub c, is going to be this times 1 over root 2, which is just 1 over the square root of 2. This is equal to this function evaluated at omega equals omega sub c. So that's 2 over the square root of 4 plus omega sub c squared. If I solve this expression for omega sub c, I get that omega sub c is 2 radians per second. So graphically, this was our magnitude response. The maximum value was 1. The value at the corner frequency was 1 over root 2, which is about 0.707, which gives us this corner frequency. For the RL example we had earlier, the magnitude response was this. We decided that the maximum value of this was 1 as omega goes to infinity. So the magnitude of h of j omega, its maximum value over all frequencies, is 1. The magnitude response at the corner frequency, magnitude of h of j omega sub c, is equal to whatever this maximum value is times 1 over root 2, which is 1 times 1 over root 2, or just 1 over root 2. That's equal to this expression evaluated at omega sub c. If I solve this for omega sub c, I get omega sub c is equal to 0.5 radians per second. So from our plot, this was our plot of the magnitude response. Its maximum value is 1. The magnitude response at the corner frequency is 1 over root 2, which is here, which leads us to a corner frequency of 0.5 radians per second. Now that I've introduced filters, I can talk about shortcuts to the math describing first-order filters. I'll do that in the next video.